This podcast is on thermochemistry. Specifically, we're going to look at heat and enthalpy and the flow of energy. We make the assumption that calorimetry and simple heat calculations are things that you remember from your earlier chemistry course. Energy is defined as the capacity to do work or the capacity to transfer heat. And of course, energy comes in three forms. We have work, we have potential, and we have kinetic energy. You've probably dealt with kinetic energy and maybe potential, but certainly not work. Work is the product of the force applied to move an object through a distance d, or mathematically, work is equal to force times distance. Well, potential energy, the energy a system possesses by virtue of its position. If you had any physics, you'll know that position could be gravitational potential energy, that the ball or book or whatever object could fall off the table and move to the floor and therefore transfer its potential energy and convert it to kinetic. That's often referred to as stored energy. It's very common in chemical systems. Kinetic is the energy associated with motion. It's 1/2 mv squared, and you would probably be able to remember some of it from the most recent gas unit. Molecules can be broken into the following three categories. All right. Energy being kinetic can be translational, meaning it's going in a straight line from one place to another. It can be vibrational, that is, motions that cause the atoms to move apart and closer in a molecule. And finally, they can be rotational, and in fact, the kinetic energy of a gas molecule is probably all three all at once. And all of them have mathematical relationships that we're not going to go anywhere near. Now, chemical energy can be converted into heat energy, it can be converted into mechanical energy, and indeed electrical energy, and we will get into that much later in the course in the concepts of oxidation and reduction. We're using a few thermodynamic terms. Thermo is heat, dynamics is flow, and heat flow is what this whole thing is all about. And heat flow is related to the conversions that take place. And the law of conservation of energy is based on this. That is, that energy can be converted from one form to another, but it cannot be created, nor can it be destroyed. The energy of the universe is constant. It is simply being converted all the time. Now, what's the difference between temperature and heat? Temperature, again, reflects the random motions of the particles and is related to the kinetic energy of the system. Recall the kinetic molecular theory and gas behavior that we just completed. Heat, on the other hand, involves the transfer of energy between two objects due to a temperature difference. And how do you think the heat flows? From an object of higher temperature to an object of lower temperature. Where does it flow? It may flow between the system and the surroundings. The system is that part of the whole thing that we normally focus our attention on, usually the chemical changes that are occurring. The surroundings are everything else in the universe, and that may indeed be the simple beaker that you are carrying out the reaction in and everything around it. Universe energy equals systems plus surroundings. The total energy of the universe is constant. If the system gains energy, the surroundings lost it. If the surroundings gained energy, the system lost it. They're opposite and equal. We have to define a state function. A state function are the conditions that make up the state of a system. It depends only on the present state of the system, not how it arrived there. You're watching the podcast in some location, and that is a state function. Where you are has no bearing and is not dependent upon how you got to where you are. It is independent of pathway. State functions are independent of pathway. When a state function changes, when you're moving from one state to another, then you simply look at the difference between the two states, and the process or the path or the way you got there doesn't matter. the distance from your home to school does not change whether you go one way or another way. It doesn't matter. The distance is always the same. Those are, in a sense, state functions. Thermodynamics. We turn this around and state these as laws. First law of thermodynamics is that the energy of the universe is constant. That is, energy is Q plus W, or heat flow plus work. If there is a change in the internal energy of a system, okay, that is the kinetic and potential energy of everything there, then it can be summed up as being some heat was transferred and some work was done. The internal energy of a system can be changed by a flow of both of those. One of them, but not neither of them. Thermodynamic quantities always have a number indicating a magnitude and a sign. The sign indicates the direction of flow. We are always with the system. That is why if energy is flowing out of the system, delta is negative. Into the system, change in energy is positive. Work. Work, as we said, was force through the distance. Since pressure is force per unit of area, work is pressure times volume. Specifically, the work that a system may do is negative P delta V. That is, there would be a change in volume. If delta V is positive, then the gas is expanding against an external pressure. Energy flows out of the system, so work is negative. The opposite is true if the change in volume is positive. The gas is contracting. The surroundings are pressuring the system. Energy therefore flows into the system, so work is positive. Now, fortunately for us, almost all the reactions we are going to do will not involve a change in pressure, and therefore no change in work. Enthalpy.